Hello class, in this lesson we're going to learn about three-dimensional space. So as a warm-up, we're going to draw some pictures. So start off by drawing a point, and then draw a plane that contains that point. So try that, and then I'll show you my drawings. So hopefully for a point, you just drew a dot. And for a plane that contains that point, usually draw something like a parallelogram to give it some perspective. Remember, a plane is just that flat surface that extends infinitely in all directions. I'd like you to add to your picture. I'd like you to draw the line that lies on the plane, and a line that only intersects it at that point that you drew. So a line that lies on it, just drew it in the middle of the plane, all solid color, all not dashed line or anything. And the line that intersects it, now you gotta be a little bit careful with how you draw it. When you have a plane overlapping a line, you usually draw that piece to be dashed. So it might be kind of hard to see what's going on here. This line is puncturing the plane at a single point. So let's look at this in 3 dimensions. So here we have the same drawing, but now in 3D. So A is our point, and here's our line that's going through it. And if we change the perspective, we can see that that line only intersects that plane one time at A. Depending on the perspective, the way the lines look is going to change. And notice that whenever our gray plane is overlapping the line, you get those dashed parts of the line. That's a pretty standard convention. Next, we're going to answer some questions involving this right rectangular prism. So remember, all the faces are rectangles, and all of the angles we have are right angles. We're comparing edges that intersect, right? And we want to figure out what's the length of AC prime. So from corner to corner, how long is that? Now, it might be hard to visualize, so let's go back to GeoGebra. And so what we're looking for is this distance right here, from A to C prime, so this diagonal distance across. So depending on the perspective, you might be using different triangles that could be helpful with this problem. So see if you can figure out how long that distance is, and then I'll show you my solution. So hopefully you notice on the bottom here, you have a 3, 4, 5 right triangle. And if we look back here, that would be if we look top down, 3, 4, and then 5 would be that diagonal. And so we have a right triangle here where 2 of the legs are the same, so it's isosceles. So you know it must be a 45, 45, 90 right triangle. So the hypotenuse would just be 5 times the square root of 2, which is about 7.07. And if we use the distance tool here, we should verify those measurements. So here for this diagonal, we get 5. And for the one from corner to corner, we get 7.07. So that checks out. Oops. Sorry, I moved my point there. 7.07. So now we're going to answer some questions using the same rectangular prism. Would you say that those lines are parallel? Why or why not? Well, they're both perpendicular to the same line, so they must be parallel. And if we look at AB and A prime B prime, look at those lines, we will see that in our model, they do not appear to ever intersect. So those are parallel. Okay, are those lines on the same plane? Well, one way to tell if they're on the same plane is to draw a triangle using 2 points from one line and a third one from another. And that triangle is going to define a plane. And is our other point on that plane? Yeah, A prime is on that plane defined by this triangle. They're all on the same face. So yes. And we can name that plane by using those 4 vertices. You need a minimum of 3, but you can use 4 if you want. And will line AC ever run into the top face? Well, if we look at our model, it doesn't appear to be true. Right? That line doesn't look like it's ever going to cross that face, so no. And those faces are parallel, so that will never cross. Right. Can we say that all of the faces are parallel to each other? No, only the opposite faces in this case are parallel to each other. And would you say that that line is perpendicular to the base? Yeah, well, it's perpendicular to these other lines on the base, so it should also be perpendicular. And is there any other line going through B that's also perpendicular to the base? No, that's the only line that gets the job done. Any other line you try to draw will be the exact same one. So that's the unique line that does the job. And what's the distance between the top and bottom faces? Well, it would just be the height, right? So we could measure the length of any of these segments. So it would be 5. Do those two lines meet? Would you say they are parallel? So lines A, B, and B prime, C prime. So AB is there, and B prime, C prime is up here. And it doesn't look like those two lines are ever going to meet. But would you say they're parallel to each other? Well, no. If they were on the same plane, they look like they'd be perpendicular. So we want to give them a different name. We don't want to say they're parallel, but we also don't want to say that they intersect. So there's a different name for that relationship. And could those lines be on the same plane? Well, let's see. If we try to draw a triangle between them, like look at the one we had before. So A, B, and B prime gives us this triangle, and that gives us this face over here. A, B, B prime, A prime. And C prime is not on that face. So no, these lines are not coplanar. They cannot be on the same plane. And finally, a line that intersects this plane. So we want to just intersect at one point, so BC, that'll get the job done. And a line that will not intersect it, so it has to be on a parallel plane. So pick any line that's on this opposite face. You could have said line CD. So now we're going to look at different properties and draw diagrams for each one. So we're going to see what we learned in 2 dimensions and see how it holds up in 3. What we have to add or tweak. So first, if we have 2 points, we can figure out the distance between them. We can draw a segment, array, a vector, or a line. So draw 2 points and draw a line that passes through them. Here's one example. Pretty much the same. 3 non-collinear points, so points not on the same line, determine a plane. And on that plane, you will have a triangle. So sketch a triangle on this plane and label the vertices A, B, and C. Here's one example. So when we have 2 lines, there's 3 different situations. Either they meet at a single point, they are parallel to each other, or they are skew lines. That is, they don't meet, but they're also not parallel. So first, let's draw 2 lines that meet at a single point. Here you go. Part B, 2 lines that are parallel on the same plane. Looks like that. And a pair of skew lines. So try to draw that, and then I'll show you my little picture. Okay, so here's my diagram. If we want to look at that in 3 dimensions, here we go. So this line that's puncturing the plane, passing through A, it doesn't intersect this other line that we have here, but it also doesn't look like it's parallel. So that's what we call a pair of skew lines. And here we have the parallel postulate. So we have a line and a point that's not on it. There's exactly one line that you can draw through the point that's parallel to that original line. So see if you can draw that line that satisfies the conditions. So there we have it. Draw your little chevrons on there. Now, when we have a line and a plane, there's a few different situations that could arise. The line could be on the plane. It can meet the plane in a single point, or it could not meet the plane. It would be on a plane parallel to it. So try to draw A, sketch the line on the plane. There we go. Part B, sketch a line that meets it at a single point. I drew this before. And a line that does not meet P. So you kind of want the line to overlap the plane to show that it's not on it. Well, this is my drawing, and I'll show you that in 3 dimensions. So here's our line. And if we look at it from the side, it's clear that that does not lie on the plane, but it's also parallel to it, so it's never going to cross it. So that's that third situation. Now, just like we talked about intersecting lines, we can talk about intersecting planes. If two planes meet, they meet at a single line. And if they don't, then they're called parallel. So draw two planes that meet at a line. Here's an example. There's a slightly different example. Here you have two planes that intersect. And if you notice, they only cross at that single line that we have over here. And that was orange or gold. And two lines that are parallel, like we saw the opposite faces in that rectangular prism. Draw two overlapping parallelograms, make one dash so it looks like it's underneath it. And here's an example in 3 dimensions. These two planes are parallel. Angle's pretty much the same. So draw an angle on this plane. The definition of perpendicular is the same. And we also say segments or rays are perpendicular if the lines that contain them are perpendicular. So try drawing examples of perpendicular lines. So there's lines. Here's rays that we extended to show that the lines do intersect and make right angles. So to say that a line is perpendicular to a plane, I want to show that they intersect once and that that line forms a right angle with the surface of that plane. So draw an example of a line perpendicular to this plane P, and then draw several lines that go through the plane and the points. So there's an example of what we're talking about. There's our perpendicular line L and some lines that go through it. And see that in 3 dimensions. Here we go. So perpendicular line and lines that go through it, or go through the point where it meets. Okay, we had this property for lines. It also holds for planes. If two planes are perpendicular to the same line, they are parallel. So draw a line here that is perpendicular to each of these planes. So here's my example. And if we look at that in 3D, oops. So we'll just be talking about this line. So this line BA, it's perpendicular to each of those planes. And if we have two lines perpendicular to the same plane, they're parallel. So try drawing those on this plane, and I'll show you my solution. Here's one example. And going back to GeoGebra, here we go. Those two lines, those look parallel, and they in fact are. And they're both perpendicular to our plane. So if we draw segments that are perpendicular to parallel planes, they will have the same length. So we draw on these perpendicular segments here. What we know about A, B, and DC. AB is equal to CD, or DC, doesn't matter. The order, and if we look here is an example of that. These are both 4. The length of the segments is 4, and if we were to move this point, we'd see that those distances are still the same. No matter where we put them, those are going to be the same number. And to figure out the distance between a point and a plane, it's going to be the length of the perpendicular segment from that point to the plane. So try drawing a perpendicular segment from A to P. That's going to represent the distance, that length. And if we look in GeoGebra, here we have an example of that. That distance is 4. And if you notice, if we move this point where it intersects, if it's not perpendicular, it's not going to be the right distance. It's going to be too long. So the distance is defined to be that height, essentially, from A to the plane. So 2 points still give us a line, 3 points still give us a triangle, and a lot of other properties are very similar to what we had in 2 dimensions. Just the relationship depends on whether or not the lines are on the same plane. So before we had parallel lines, but now there's the case that we can have skew lines. So and here's a couple vocabulary terms to help review. In this video, we learned about properties of 3-dimensional space. Thank you for watching this video.